So again, just try and come up with the functions that yield these different derivatives here. Okay? While you do that, I'm going to pass back some papers that I've been holding on to here. Get some of these things back to you. These are old quizzes that I just never got back to. You already see them? Yes. I just never got them back. There are people who still haven't finished them. Yes, there. Now yours is put up on your image. Got that.
I did last year. I'm going to rate your classes. I don't care. I get a nice note. What is it? I'm not doing it.
Later, I probably thought about like just huh? No, it was like before you look at it. Yeah. I thought about it and I was like, go later when I drove past it. There's a girl. I saw a girl that was like yeah.
All right, like 30 seconds here. We're going to be going over this. 30 seconds. Okay. This is on last term, though, too, there, Madison. So, and then actually, I still have yours. I got a grade. Okay. All right. Whew. Here we go. So, let's get into this further now. All righty. So, number one, what function, when you take its derivative, gives you 2x? X squared, okay. Okay, what did I hear? Plus c. Why? What's that c for? A constant. So what do you mean by that, though? Right, so like we could say x squared is our answer here, right? The derivative of x squared is 2x, but if I add like a 2, right, wouldn't the derivative of x squared plus 2 also be 2x? Right, or x squared plus 3, or x squared plus 10, or x squared plus e, or x squared plus pi. Okay, so to give a more kind of like accurate representation of what this original function could be, it's not a bad idea to put a little plus c on there at the end, where c is a constant. Okay, our old friend c. Okay, c is a constant there. Right? So while x squared is certainly an answer, it's a possible answer. If we want to kind of represent all of the possible answers whose derivative is 2x, we want to give this kind of x squared plus c. Okay? So if you gave x squared, that's fine. But in this case, really, the more general answer is x squared plus c. Okay? So what about f prime of x equals 6x squared? What would its original function be? Okay? It would be 2x to the third. And again, if you want to put the little plus c on there at the end. Okay? Very good. What about cosine of x? What is its original function? Sine of x. And again, we can put a little plus c on at the end there. Okay? What about e to the x minus 3? E to the x minus 3x plus c, right? The derivative of e to the x will give us e to the x. The derivatives of minus 3x will give us just minus 3. And of course, the derivative of a constant is 0, so it's gone there. Okay. What about 1 over 1 plus x squared? Arctangent of x. Yeah. Those inverse tangent. Yes, plus c. This inverse tangent. Inverse trig derivatives. Fun times. All right, and then how about this one? Natural log of 2 minus 5x plus c, right? The negative 5 we're going to get because what's the derivative of natural log of something? It's 1 over that something. 1 over 2 minus 5x. Then times the derivative of what's inside. The derivative of what's inside here would be a negative 5. So there's where that negative 5 comes from. Okay, and then plus the c. Okay, so this next little sentence here, okay, we kind of like already mentioned this, but I'll say it again just for the purpose of going through the notes here completely. All right, the function, capital F of x, is an antiderivative of f. So all these functions that we came up with here, okay, these are called antiderivatives of the original function, or I guess of f prime there in that case. On an interval I, if, so we know something is an antiderivative of something if capital F prime of x is equal to little f of x. Okay, so if we take its derivative, if we take the derivative of capital F here, and we end up with that f prime, which is equal to little f, then we know that's the antiderivative. Okay, so if you can take the antiderivative of this, match it back to this, that means it's an antiderivative of this original function that we had. Okay, remember that f is an antiderivative rather than the antiderivative because any constant c could fill in here, right? So there's an infinite number of solutions here, okay, depending on what value c is, okay? We can kind of like come up with a c value right now, okay? So we call these solutions, okay, well, I guess we'll come up to that in a second here, so I'll hold off on that, okay? So let's find the antiderivatives of some of these things right here, right? Okay, what is the derivative of, not antiderivative, let's just find the derivative of these things here. So what is the derivative of x squared, for example? 2x, right? Okay, what's the derivative of x squared plus 5? What's the derivative of x squared minus pi to the e? 2x, because again, pi to the e is just a constant. Okay, so you'll notice that all three of these different functions, okay, have the same derivative. Okay? But they're antiderivatives, right? They're slightly different. They all have the x squared, but then they have different constants and stuff like that, okay? And so we can represent all of the possible antiderivatives of this 2x as just saying the, let's see here, I guess I'll say capital F of x equals x squared plus c. Okay. So which, again, just kind of re-emphasizing what we've already stated earlier there. Okay, we jumped ahead a little bit by saying that plus c stuff, but that's okay. Okay. All right. If we want to represent all of the possible antiderivatives of 2x, then we want to put that plus c on at the end when we find the antiderivative. Okay. The constant c is called the constant of integration. Okay. The process of finding that antiderivative is also called integration. All right, and so when we come up with that c, it's the constant that arrives kind of with that integration. Okay, the functions represented by capital F is called the general antiderivative of f. Okay? And capital F of x equals x squared plus c is the general solution of the differential equation f prime of x equals 2x. Okay, so that's a lot of vocabulary we're throwing at you here, so let me just break it down real quick for us, okay? Again, c is the constant of integration, right? C is a constant, and it just shows up when we integrate or find the antiderivative, okay, of a function. Capital F, okay, is known as the general antiderivative of f, okay? So in other words, the way we kind of denote the antiderivative of a function is we capitalize the function's name, right? The way we denoted taking the derivative is we took that function f and we put a little apostrophe with it. In integration or in finding an antiderivative, we just capitalize it to show that it is the antiderivative of the original function f, okay? We go kind of backwards. And then finally, capital F of x equals x squared plus c. Okay, this particular example we were mentioning right here, right? It's called the general solution, right? General because it's got a plus c there, so it could be a lot of different options. Okay, solution to this differential equation. Why is this thing a differential equation? Well, because it's got an equal sign, so that makes it an equation. And differential because it's a derivative relating in here. Okay, so every derivative that we've come across, with an equal sign in it, it's a differential equation. How do you solve the differential equation? You integrate, you find the antiderivative right here, and this is called the general solution. And later in this class, we'll be finding particular solutions too. Finding c values for the particular solutions. Yes?
On mine, my f of x in the last after differentiation is lowercase. Isn't it?
On yours, the f of x in, sorry, which? Oh, I see what you're saying. Equals 2, equals little 2. Okay, I see what you're saying. Yes, because little f, in this case, is the same thing as capital F prime of x. So it's the same. It is the same thing. So, but you have a different version of notes where it was changed to little f of x, and I have capital F prime of x here. Okay, but it is the same thing. Little f, right? And you take then capital F. That's its antiderivative. Is the same idea here. Capital F prime and f of x there too. Okay, so it's the same. It's the same kind of thing we're talking about, I guess, if that makes sense. Capital F prime, that is lowercase f, and vice versa in our way we denote things.
So I get the difference between big F and little f.
Uh-huh.
I don't get the difference between big C and little c.
So big C and little c, there isn't a difference. They're the same thing. Sometimes we just capitalize the c, and I'm not doing a very good job of capitalizing it there. It doesn't matter. It's just c. That's all it is. So, good question. I'm glad you asked it, though, just to make sure. Okay? All right, so notation for antiderivatives. The operation of finding all solutions of this equation when you find an antiderivative is called antidifferentiation or indefinite integration. Okay, and we'll talk about indefinite integration and definite integration a little bit later too. Okay, and is denoted by the integral sign that. I don't have a name for that. I don't know what that thing is called. Okay, but that's the integral sign. Okay, the general solution is when we integrate f of x dx, that is equal to capital F of x plus c. So again, f, remember, you can think of that as like the derivative of capital F, and then we've got our antiderivative right there. Okay? So you integrate a function, you get its antiderivative. The expression integral of f of x dx is read as the antiderivative of f with respect to x. So dx serves to identify x as the variable of integration. Okay? The term indefinite integral is a synonym for antiderivative. Okay? So, indefinite integral is the same thing as saying antiderivative. They mean the same thing. Okay? Whew. Good stuff. Moving on. Okay, moving on. Okay? Some basic integration rules. Okay? So, sure here. I think I printed out. Okay, yes, mine is slightly different here, so I will. Okay, it's pretty close to this one though, for right now. So the inverse nature of integration and differentiation can be used to obtain, and mine's just down here. Okay, yours is like over here, I think, right? But mine's just down here. Okay, and actually, here's what I'm going to do because I realized that the copy that I printed off is slightly different, so I'll just use someone else's notes here and fill them in for them. Okay, we'll just do that. So that way we're all looking at the same thing here. Okay, there we go. Okay. So the integral of the derivative of a function is equal to the original function itself, right? And that's what we kind of already saw on the front, right? We found the oh gosh, this is going to be really complicated. No, let's do that. We had derivatives, and we found the antiderivatives, and that gave us x squared plus c there, right? So another way of writing this is we could say that the integral of 2x dx is equal to x squared plus c, right? We integrated f prime, which is 2x, and that yielded x squared plus c, the original function. Okay, that's all that little thing is saying there on the next page. Okay. So, additionally, if the integral of f of x dx is equal to capital F of x plus c, then and not a capital. That should be a lowercase, I think, actually. Let me do it this way. No, it should be capital F of x. Sorry, it should be capital F of x. Okay. So it should be a capital there. If the integral of f of x with respect to x is equal to capital F of x plus c, that antiderivative, okay, then we can take the derivative of an integral. Okay? If you take the derivative of an integral, those are inverse operations. They cancel each other out. So taking the derivative of an integral yields the exact same function as what you have inside. Okay? Okay? Just like if you take a number like, 3, and you square it and then take the square root, we end up with just 3. Right? Okay? And they cancel each other out. The square root and the square cancels out. In the derivative of an inverse, they are inverse functions. The derivative of an integral, they are inverse functions. They cancel each other out. And so you're left with just f of x there. Okay? So, what is the antiderivative of each of the following? Try to develop the basic power rule for integration. Okay, so we have a power rule for taking the derivative, right? The derivative of like x to the n we have as being n times x to the n minus 1, right? That's the derivative rule. Try and come up now with a power rule where if you take the integral of x to the n with respect to x, what does that equal? Okay, and you have a little space down here to fill that out. So try and come up with the antiderivative of these three functions. See if you can come up with a general rule then for the power rule for integration. Okay, so go ahead and take a minute to do that. So try and come up with the functions whose derivative is x squared, or come up with a function whose derivative is x cubed, or a function whose derivative is x to the fourth. Okay? Anti-differentiate, or integrate here. It's kind of used, like we use it to name the antiderivative of a particular function. Okay? So like if lowercase f of x equals x squared, the antiderivative, or if you integrate this, you would name that as capital F of x equals that. That's the antiderivative. Okay? It's just like when we took the derivative of something, right? The name of the derivative was f prime of x. That showed the first derivative of this function. Capital F of x then is the one step up from that. One step up from that. It's the antiderivative or integral of f of x, lowercase f of x. That's why we use the capital F there to describe it. Okay.
So are the two ways of writing it kind of interchangeable, or?
Well, like you use the integral symbol?
Yes.
Yeah. I mean, it's the integral symbol. Like this is capital F of x. You could say that is capital F of x, or you could just say this. Like either way
The
of
two
writing.
ways of writing them, could I write it?
Yeah.
Okay.
The most typical way we're going to be writing it is this way because this. I don't know. That's just a more typical way we're going to be writing it. But sometimes it is described. This way.
Okay.
But generally, we're going to be using this way for the most part. Okay, the last one here. Please do not forget to write these dx's as well when you're integrating. Okay, it's very important because you are indicating to the person who's grading your paper with respect to what variable you are integrating. Okay, so make sure that you write that dx. It is necessary. Okay, it is necessary for good math. All right, so the power rule for integration is, and this is going to be the plain English here. So what should we do? What happens to our exponent? Clayton?
I said 1 over n plus 1 times x to the n plus 1.
Okay, yeah. So we add 1 to the exponent and divide by the new power. Or more officially, more precisely, x to the n plus 1 over n plus 1, and then of course we put a little plus c at the end there. Okay, that is our power rule here. The integral of x to the n with respect to x is x to the n plus 1 over n plus 1 plus c. Or you could write it as 1 over n plus 1 times x to the n plus 1 plus c, like that. Either way is acceptable there, right? They're both the same thing. Okay? Questions? Yes? That is the integral symbol. Integral symbol. I don't know what the actual name for that symbol is, but as far as I know, it's just the integral symbol. Yeah, that's as far as I know. Okay? It's not some Greek letter or anything like that. Yeah. You mean whether we use the integral symbol or whether we use capital F of x? I will say the majority of the time, it would depend on kind of the way the problem is presented to. The majority of the time, we're going to be writing it like this. So I would say this is more the typical way that we write it. And you could, this is not wrong to give the answer in this form, I would say. But typically, we write it with the integral symbol there. Because it's like the symbol we use to kind of show the operation of integration. This isn't really showing the operation of integration. It's showing that this thing is related to little f as the antiderivative of it, but it doesn't give an operator, kind of thing. This is like an operator. It like shows us like, hey, this is the thing we're going to do. So anyway, yeah.
So you
Morgan?
use like the integral sign and then like the original function that you're trying to find the derivative of, and then dx. Is that like always?
So the thing you're trying to integrate. So this is like more typical of like what you will see as like a problem. We are going to integrate this thing. And so we want to come up with its antiderivative, okay? You could say, in other words, that this thing right here, lowercase f of x, is x plus 2, and we want to find capital F of x. What is that, right? That's kind of what this is asking in so many words, okay? So let's use that. Let's use our little power rule that we talked about now to come up with these antiderivatives, to integrate these things, okay? So the integral of x plus 2 dx, okay? Well, as it turns out, just like we can differentiate over a sum, we can also integrate over a sum. So in other words, it's the same thing as saying the integral of x dx plus the integral of 2 dx. Okay, so we can integrate these things individually. So this is x to the 1. So when we integrate x to the 1, what's the new power of x going to be? X to the 2, okay, over that new power. So x squared over 2. Or you could say 1/2 x squared there if you wanted to instead. Okay? What's the integral of 2? Or in other words, the derivative of what is going to give us just 2? 2x, right? So plus 2x. Okay. You can also think of this as the integral of 2x to the 0, right? Isn't that the same thing? 2 times x to the 0 is the same thing as 2 by itself. And so we add 1. We add a power, add 1 to our power here. So 0 plus 1 is 1. So we get x to the 1 here. And then divide it by 1, so it's still just going to be 2x. So it follows the power rule that we established already. And of course, don't forget your plus c at the end for our answer. Okay. Or if you prefer to not have the x squared over 2 like that, you can make it 1/2 x squared plus 2x plus c. Yes?
Could you also treat the binomial like as a binomial and just say 1/2 as a binomial to the second power?
So that is kind of like trying to do what I would call like a chain rule, right, in reverse. And we do kind of have a way to the chain rule in an integral, but we're not quite there yet. And so I would not do that yet. Yeah, we want to break it up first. Okay, and we'll take a look more at that in just a second here. All right, let's look at this. Integral of dx. What is the number in here we could put? A 1. So we could say this is really the integral of 1 dx. And again, whose derivative gives us 1? The derivative of x, right? So this answer is just x. Of course, don't forget then the plus c at the end there. Okay. Again, you can think of 1 as really being the integral of 1 x to the 0. We can use that power rule there, add 1 to our exponent and divide by 1, and then just 1 out front there. So 1 x to the 1 over 1, which is really just x plus c again. Okay? So another way to think about it there. Okay? All right, and we'll do the same thing here, integrate here. So the integral, so t to the 4th is going to become t to the what? 5th over 5, and then there's still that 3, so we'll just make it 3t to the 5th over 5 like that. Okay, just like when you take the derivative and the coefficient just kind of comes along for the ride, same thing here. When we take the integral of something, the coefficient kind of just comes along for the ride. Okay, minus, okay, t squared, when you integrate that, it'll become t to the 3rd. So it'll be 5t to the 3rd over 3, okay, because again, you divide by that new power, plus, and this is t to the 1, so t to the 1 becomes t squared, and then divide by the new power 2, and then again, plus c. Okay, or in other words, you could say 3/5 t to the 5th minus 5/3 t cubed plus 1/2 t squared plus c. Okay, now, the nice thing about these integrals is that you can check whether you did it correctly or not. Okay, how do we do that? How can I check to see if I did this right? Take the derivative and see if you get this. All right? But who likes to check their work, right? I mean, your teacher always tells you to check your work, but you never actually do it because you know you got it right, but then you end up getting it wrong, and your teacher's like, why did I not check my work? And then, so I'm just going to show it to you real quick here. 5 times 3/5 is 3t to the 4th there. 3 times minus 5/3 is minus 5t squared. And then 2 times 1/2 is 1, so plus t. And then the derivative of a constant is 0. It goes away. Whew, I did it right. I did it right. Good job, everybody. Okay, well done. Oh my gosh. Yes, we're going to fill this in right now. Okay, so you guys go ahead, take like 1 or 2 minutes and fill in all of your differentiation rules right here. Fill them all in. You guys know these derivatives, right? Even the derivative of a to the x, Mr. Wig? Yeah, even the derivative of a to the x.
Oh, so you just want like regular derivative?
Yeah. Give me the derivative formulas, and then we'll go over the integration formulas here. Okay? You will pretty much have an idea of what the integration formulas are going to be, but just don't quite fill in the integration formulas yet. A few of these are not going to maybe be what you think they're going to be. Okay? So do the differentiation formulas. These are all things you should know. Take a minute or two. Go ahead and do those. I'll do them too, real quick here. Oops. Yes, Shelby. Yes. Try to trick you. Just kidding. Yes. Derivative of secant, derivative of cosecant is negative cosecant cotangent. Just like the derivative of secant is secant x tangent x. So the derivative of cosecant will be negative cosecant cotangent. And then cotangent, which is like tangent then, right? Those are where you get the cosecant squared and the secant squared. I could do those hard trig ones. This is the k times x. What is that? Who knows? Okay. Who knows? All right. So there are our derivatives, right? We've all become like hopefully super familiar with those, right? And for like this whole section of calculus that we've been teaching, right? Whenever I ask the question, what should we do here? You guys at least should be able to answer. We're going to differentiate. And now we're introducing integrate, and so we're going to now have two options when I ask you a question. Do we differentiate in this situation? Do we integrate in this situation, right? That's going to be kind of like the new kind of answer we can come up with here, the new calculus topic. Okay, so the derivative formula that we have here is that the derivative of k times x is equal to just k, right? The derivative of 3x is just 3, 2x is just 2, so on and so forth. So then if we integrate k with respect to x, what will our answer be? In other words, if we integrate this derivative, what should we go back to? Kx, right? Plus c. Okay, and that's going to be kind of the pattern for all these integration formulas here. We're going to be integrating all of these red derivatives that we have, or that I have written down here. We're going to integrate those and kind of go backwards to the original thing whose derivative we took. Okay, so same thing here. We're going to integrate k times f prime of x with respect to x, and so we should end up with kf of x plus c. Okay. All right, same thing here. We're going to integrate this sum. We're going to integrate f prime of x plus or minus, or difference, I guess, some more difference. F prime of x plus or minus g prime of x dx. So the integral of these derivatives should be back to the original functions, f plus or minus g of x. And again, don't forget the plus c, though, at the end. Okay. If we integrate n, actually, no, I'm just going to not do this one. This one's going to be slightly different here. We're going to integrate x to the n. Okay, our more like typical, this is our power rule here. Okay, the integration power rule. Okay, when we integrate x to the n, what happens to n? When we take the integral, what do? I hear -1, I heard +1. +1. We're going to add 1 to our power. So x to the n plus 1 over n plus 1 plus c. Again, or if you like, 1 over n plus 1 times x to the n plus 1 plus c. Okay, either one of those is acceptable. Same thing, right? All right, so that one was slightly different just because we wanted to have that general power rule there. Okay, this one's going to be a big one right there, of course, for us to remember. We just learned that one too. Okay, all right, let's continue with our trig stuff. So the derivative of sine is cosine, so therefore the integral of cosine of x with respect to x is going to be sine of x plus c. Okay, very good. The derivative of cosine is negative sine, so if I integrate positive sine of x, what should its integral be? Negative cosine of x plus c. Okay? We're going in reverse here. We integrate sine to get negative cosine. We integrate cosine to get sine. Okay? All right? If we integrate secant squared of x with respect to x, then we should get what? tangent. Yeah, tangent of x plus c. And if we integrate secant of x times the tangent of x with respect to x, then we should get what? Secant of x plus c. If we integrate cosecant x, cotangent x, question?
Why isn't sine negative on the right side when we integrate cosine?
Because right here,
Yeah. Why isn't?
why did I make this sign negative?
Why didn't you?
Because I could have. If I made that negative sine of x, then I would have gotten a positive cosine of
Aren't you just like doing it?
We're kind of like, I guess I could have done it that way, I guess, because sometimes you'll also just run across a positive sign, so make it negative cosine. But if it was integrating negative sine, then certainly it would be a negative cosine, which becomes then positive cosine of x when you integrate it. So yes, it would be positive cosine if you're integrating a negative sign there. Okay? So yes. I just write it that way because that's the way it's presented. I hear what you're trying to say, Emma. We're going backwards, right? So why don't we just use the integral of, negative sine here and then say it's equal to cosine? And that's true, but for whatever reason, the book likes to leave it as a positive. And then if there's a negative in there, you just then make your answer negative. Or opposite, I should say, too. So, anywho, integral, again, same thing here, Emma, too. The answer is negative cosecant cotangent, but we're going to integrate positive cosecant cotangent, which will result in then a negative cosecant of x plus c. Okay? And then let's see here. We'll integrate cosecant squared of x dx, which then is going to be a negative cotangent of x plus c. Okay, easiest integral of our life. What's the integral of e to the x? E to the x, good old e to the x. He's really easy to integrate. Okay. All right, and now we want to be, we're going to integrate a to the x dx. Okay, the integral of a to the x dx is 1 over the natural log of a times a to the x plus c. Okay, 1 over the natural log of a times a to the x plus c. And then finally, if we integrate 1 over x, this is equal to the natural log of the absolute value of x plus c. Okay. It's important here that we include those absolute values because the function 1 over x does not have, or its domain includes both negative and positive x values here. But then when you integrate it, okay, the natural log, in order to be able to include that domain that we had from here, we need to put an absolute value, right? Because we can't take the natural log of negative numbers. And so we want to exclude, we don't want to exclude the domain values here, so we want to make sure that we put an absolute value around that to allow us to be able to take evaluate the natural log of those negative x values. Okay. One little thing I want to mention here. Actually, questions on any of these formulas before I give you that. Okay. One little thing I want to mention here. 1 over x. Okay. Just like if you remember when we first started talking about derivatives, sometimes we had to rewrite our derivatives before we could then take the derivative, rewrite our functions before we could take the derivative. The same will be true here in just a few moments. For our integrals, we're going to see how we do that. But when we see something like 1 over x, the temptation is to rewrite that as x to the negative 1. Right? Because that's true. It's true. But then the temptation is, aha, it's a power rule. Right? So when we add, if we use our power rule to this, we're going to have x to the negative 1. We're going to add 1 to that power, so it becomes x to the 0. And we have to divide by our new power. Uh-oh. We're dividing by 0. Okay? And so, please, this is not a power rule. Okay? Okay, not a power rule. Use that, okay, instead. Okay, so x to the negative 1, if you try to integrate that using our power rule, you're going to get x to the 0 over 0. But x to the negative 1 is really 1 over x, whose integral is natural log of the absolute value of x plus c. So please be careful with that. Now, x to the negative 2, this is the power rule. Okay, x to the negative 2, that is a power rule because we can add 1 to this, and we get x to the negative 1 and divide by the new power negative 1, and then, of course, plus c. This is okay. In fact, this is right. The integral of x to the negative 2 is x to the negative 1 over negative 1 plus c. Okay? But this is not right. Okay? Do not do this. Okay. All right, moving on. Let's get into some of these example problems here. All right. So the most important step in integration is rewriting the integral. Even more so than in the derivative, than when we did in the derivative, right? Okay? Because the integral is even more finicky about being in the correct form for us to integrate, right? So, for example, 1 over x to the third, okay? We do not have, this is a quotient, right? We do not have a quotient rule for integration yet, nor will we actually ever come up with a quotient rule for integration. There isn't one, okay? So we must rewrite this into a form whose integral we can, complete. So how should we go about rewriting 1 over x cubed? X to the negative 3 dx. Okay? And then we use our power rule here, so we're going to add 1. So what's our new power going to be? X to the negative 2 over negative 2 then, right? Because we divide by the new power, plus c. Okay? And then I'm going to simplify that. So that's equal to that, equal to that. And so we have negative 1 over 2x squared plus c, like that. And there's our final answer. Okay? Or you could have 1 over negative 2x squared if you wanted to, plus c. Okay, questions on any of that? Okay, let's look at letter B. Square roots, right? We've seen these show up in derivatives. We always rewrite a square root as x to what power? 1/2. But since it's in the denominator, we're going to further rewrite it as x to the negative 1/2, okay? And so we'll leave the 1/2. We still leave that 1/2 in front there, but that's equal to x 1/2 x to the negative 1/2 dx. Right? All we did was take the x out of the denominator, so only x is being raised to that negative 1/2 power there. The 1/2 is still there. Okay. And again, this is a power rule. That 1/2, that coefficient, we can ignore it or just kind of bring it along for the ride. Okay. What is the integral of x to the negative 1/2? What do we do with our power? Add 1, so what's negative 1/2 plus 1? X to the 1/2. Okay, 1/2 x to 1/2 over, we divide by that new power, 1/2. And of course then plus c. Okay, so we had the 1/2 already in the integral there. And then we divide by 1/2 because that's our new power there. Now what happens to these 1/2s in front here? They cancel. And so we're left with the square root of x plus c, or x to the 1/2 plus c, if you prefer to just leave it. Like that. Okay? Questions on that so far? All right, letter C. Can we take the integral as it's written here? No, it's because why? It's a product. And do we have a product rule? Nope. And will we ever learn one? Actually, no, not really. So, what do we do here? Distribute. So we get 6t to the third minus 18t squared plus 2t dt. Okay, equals. Okay. Notice we are integrating with respect to t here because our variables are t, right? Okay, but no different than x's. We just kind of do our work here. So the first term, 6t cubed. Okay, t cubed becomes t to the, so it'll be 6t to the fourth over 4. T squared becomes t to the third, okay, over 3. So it'll be 18t to the third over 3. And then plus 2t squared over 2. And don't forget again our plus c. Okay, and then we'll simplify this. 6/4 becomes 3/2 t to the fourth. 18/3 is minus 6t to the third. And then 2/2 becomes just 1, so plus t squared plus c. And so there's our simplified version right there. Okay. All right. So next one, integral of y squared plus 1, quantity squared. So that's the same thing. So again, here we do not, so there's no product rule. Okay, if we were to integrate this, we don't have a chain rule either. Okay, there's kind of a chain rule thing that we'll be learning, okay, called integrating by substitution and stuff like that, but we're not quite there yet, and it's not quite a chain rule. It's not quite what we want it to be. So in order to integrate this, what do we have to do? Yeah, we got to multiply it out, okay? So we're going to do y squared plus 1 times y squared plus 1 dy, and then, simplify that, so it gets y to the 4th plus 1y squared, so it's going to be 2y squared, and then plus 1. Okay? And so we integrate that, so y to the 4th becomes 1/5 y to the 5th. 2y squared becomes 2/3 y cubed, and then integral of 1 is just y plus c. Okay? And then I don't really think there's a way to simplify that, so we'll just leave it as 1/5 y to the 5th plus 2/3 y cubed plus y plus c. Okay? So far, so good there? All right. Letter E. Do we have a quotient rule? No quotient rule. So we have to divide this. Okay, so we'll break up our numerator, make it x cubed over x squared plus 3 over x squared like that. How can we rewrite x cubed over x squared? It's just what? The integral of x, right? Yeah. And then what about 3 over x squared? How can we rewrite that?
3x to the -2.
Correct. 3x to the -2. Okay, again, no integrating yet, right? We're just rewriting it. X cubed over x squared is x, and 3 over x squared is 3x to the -2 dx. So the integral of x, 1/2 x squared, or x squared over 2. And the integral of 3x to the -2, okay, so our new power is going to be 3x to the -1, right? We're adding 1 to -2, so it becomes -1 over the -1 there, the new power, plus c. Okay, and so we simplify, so it's 1/2 x squared minus 3 over x plus c. Okay, 3 over x plus c. All right. In the interest of time, I'm going to skip those next two, but I will come back to them tomorrow. Okay, I'll come back to those tomorrow. I do want to really quick just talk about the integral of secant squared is what? Yeah, tangent. Just tangent, okay? The integral of cosecant squared is negative cotangent, okay? So just understand that's how you take the integral of those. And of course, the integral of 2 over theta, it's 2 times theta to the -1, so you just use your power rule here. Here again, you'd want to distribute, just make that p to the 1/3. And we'll talk about it tomorrow, so I'm not going to harp on that too much more, okay? So far, all of our solutions we've been finding have been general solutions. That means we have that plus c, okay? There are several antiderivatives for a function depending on that c value, right? In many applications of integration, you are given enough information to determine a particular solution. To do this, you need only know the value of y equals f of x for one value of x, okay? This information is called an initial condition. So, the solution to the differential equation f prime of x equals 3x squared plus 1 has only one curve passing through the point 2, 4. So the solution to this differential equation, that is the integral, okay, has one solution that goes through this point 2, 4. Find the particular solution that satisfies this condition, then approach this graphically. And we'll hold off on the graphic part for right now, okay? Or the graph part for right now. We'll just focus on doing it with the analysis, okay? So to solve a differential equation, what do we got to do? Integrate, exactly right. So f prime of x equal to 3x squared plus 1. Okay, we're going to integrate that 3x squared plus 1 with respect to x, of course. Okay, so again, the 3's are coefficients, so what's the integral of x squared? So it'll be 3x to the 3rd over 3. Right, what's the integral of 1? X, and then plus c. Okay? So f of x equals x cubed plus x plus c, right? If f prime was 3x squared plus 1, then f of x will be x cubed plus x plus c. Okay? And again, here I'm not using the capital F because we integrated f prime. The integral of f prime is just lowercase f. If we integrate lowercase f, its integral is capital F then. Okay? So if you integrate f prime, it becomes lowercase f. If you integrate lowercase f, it becomes capital F. Okay? And that's just kind of the denotation here. Now, how can we use this point to find our particular solution? What do you think we should do? Plug it in. 2 should go in for x, and 4 should go in for f of x, or the y value. So yeah, we'll say 4 equals 2 cubed plus 2 plus c. Okay, so 2 cubed is 8, plus 2 is 10. So subtract 10 from both sides. C is negative 6. So the particular solution is x cubed plus x minus 6. This was, remember, the general solution. Okay, general solution there. Okay, right there. Okay. Let's do another one. All right. We've got the general solution. We want to find the general solution of f prime of t equals e to the t for that differential equation. And we want to find the particular solution then that satisfies the initial condition, f of 0 equals 3. Okay? So we'll integrate here. F prime of t is equal to e to the t. So the integral of e to the t dt. What's the integral of e to the t? E to the t plus c. Okay? It's like a little poem or something like that. So we get f of t equals e to the t plus c. And then what should we do with this point here? What goes in where? 0 should go in for t. So we'll have e to the 0 plus c. And then equal to 3. Okay, what is e to the 0? 1. So c is 2. So our final answer then is e to the t plus 2. Okay, and that's f of t. Whoops. Okay, like that. That's our particular solution. Just like that. Okay. The last one here gives us f prime prime. Okay. We are told that f prime prime equals sine of x plus 2. And we want to find f of x, which means we have to integrate how many times here? Twice. After we integrate the first time, we'll have 1 plus c, and we'll use this piece of information because the slope of f, that is f prime, at x equals 0 is 3. Okay, so f prime is 3 at 0. So that gives us our first c value. We integrate that to then get to our f of x, which has another plus c, and then we'll use the pi and the 1 there. And again, I don't want to squeeze that in right now, so we'll kind of stop there. Okay, but that would be the idea. So we'll finish up these two problems and this last one here, and then your homework is posted already to Google Classroom. And then tomorrow we'll get into position, velocity, acceleration. Yeah.
Mr. Whitmer, is the problem set due tomorrow or Monday?
Problem set is due Monday. Thank you for the clarification. Yeah, problem set's due Monday.
I have a question about one of the.
All right, let me finish this real quick, and then I'll get you.
Like, all of a sudden, by the time you're into that work,